All right, so here's a video 1 of 3 for our spring break notes. I'm going to do my best to keep each video under 30 minutes. This will definitely be the longest of the 3 because we have a little bit to review. So we're in chapter 7. We're not going to use the textbook. We're just going to kind of run through it with this PowerPoint. I would encourage you to take some notes somewhere, right, in a notebook or some blank sheets of paper. But I will also post this file as well. So anyways, kind of jumping into this. Hopefully this first part is review, but like I said, we have to go through the review first. So this should be review from middle school, maybe even some of it from elementary school, of different shapes. So when we have the word polygon, that word poly right there, poly means any. So gon means kind of sides or shapes. So when we see polygon, it's any sided shape, right? Any sided shape. So basically all shapes that we can name are polygons, right? Triangles, quadrilaterals, pentagons, squares, rectangles, pretty much all of those are polygons. Now circles, not quite, because circles don't really have sides, but all other shapes that we can name would be polygons. So the common shapes that we kind of want to be familiar with are anything with 3 sides, we call triangles, right? Anything with 4 sides are actually called quadrilaterals, right? Squares, rectangles are types of 4-sided shapes, so they're types of quadrilaterals, but our base, 4-sided shape is a quadrilateral. And then, pentagons, hexagons, octagons, those are probably the most common. When we say a regular polygon, it means that all sides are the same. So, a regular quadrilateral would be a square. And, anything with 8 sides is an octagon, so this stairs, you can count, you'll have 8 sides octagon. Right, jumping into triangles. Okay, again, hopefully most of this is reviewed. We can classify triangles in a few different ways. So by their angles on the right, we would have obtuse has an angle greater than 90 degrees. Right, that would be like our biggest angle is greater than 90 degrees. Acute, our biggest angle is smaller than 90 degrees. That means all angles are smaller than 90. So an example here, you have 62, 75, and 43, so all 3 angles are smaller than 90. And then right, our biggest angle is 90 degrees. So in a right triangle, our biggest angle is 90 degrees. The connection we're going to make here, as well as this, that 90 degrees is perpendicular. So we're going to make that connection. Okay, for sides, we can also do these by the sides. So in scaling, all of our sides are unequal. No sides are the same, right? So scaling, no equal sides. In isosceles, we have 2 equal sides. And in right triangles, we have 3 equal sides. Now, when we have equal sides, that also gives us equal angles. So that's important to realize as well, is we'll have equal angles as well. All right, for quadrilaterals, that's a 4-sided shape. And there are a ton of different types, right? And so one thing I want us to kind of realize with this diagram is that anything with an arrow pointing down, the shape below it is a type of whatever's above it. So, a kite is a kind of a quadrilateral. And then a rhombus is a type of a kite. And then a square is a type of a rhombus. Then same thing kind of coming down here. A parallelogram is a quadrilateral. A rectangle is a type of parallelogram. And a square would be a type of rectangle and a type of parallelogram. So that's kind of how that works. And so when we get into this, we want to make sure that we realize, what properties each of these have. So when we see the word parallelogram, this might be new to you. This one might be new to you. A parallelogram has opposite sides being parallel. These arrows, one arrow and one arrow, that's our signifying that those sides are parallel. Right? And we want to make the connection to Math 1. What did we say when we had parallel? Is that they have the same slope. So if we graphed this, those 2 lines should have the same slope. Right? The 2 arrows and the 2 arrows, same thing. 2 arrows, 2 arrows. Those 2 guys are going to be parallel. So our opposite sides are parallel. And what that also does is it makes our opposite sides and our opposite angles equal. So this, side AB, we're going to name that side as AB, right, will be equal to this side CD. right? So those two sides will be equal to each other. Now, rectangles, squares, and rhombuses are all types of parallelograms, right? If we kind of go back here, a rhombus was a parallelogram, a rectangle was a parallelogram, and a square is a parallelogram. So those three shapes will also have parallel sides, and their opposite sides will be equal, right? A rectangle is just basically a special type of parallelogram where our angles are 90 degrees, right? So we knew that the opposite sides were equal. This 1 dash and 1 dash tells us that, the opposite sides are equal. Now we could also have, the arrows as well to show that they're parallel. But then all of our angles are now 90 degrees. So we want to make sure that we make that connection, right? That if we have 90 degree angles, perpendicular has opposite reciprocal slopes, right? When we have perpendicular lines, they have opposite reciprocal slopes. All right, rhombus is a special type of parallelogram where all four sides are the same. Now, it's not necessarily a square, right? Usually when we think about all four sides being the same, we think of a square. But a rhombus can be a square that's kind of tilted, so it's not a square anymore because these angles are not 90 degrees, right? That's not a 90 degree angle. Whereas a square is a rhombus that now has 90 degree angles. So a square basically has all of those properties, right? All of the sides are equal, opposite sides are parallel, and then the property of a rectangle, which is our angles are 90 degrees. So hopefully most of that was a review. The one thing I do want to point out, a lot of times students use the wrong words, and I catch a lot of students using the wrong words. They call squares rectangles, and they call rectangles squares. And this is kind of interesting because it's kind of half true, actually. Squares, this guy would be a square and a rectangle. So you could call this guy a rectangle because squares are rectangles. But none of the other ones are squares, right? All of these other guys are only rectangles. So actually every single shape here is a rectangle, but only that orange one is a square. So that's kind of how it works. The connection I like to make is if you kind of think about it this way. All students are humans, right? But not all humans are students. Some humans are no longer students, right? Like your parents aren't students anymore. But all students are humans. Kind of the same thing. All squares are rectangles, but not every rectangle is a square. So that's kind of how that works. All right, so now we're going to move on to our new stuff. So with the new stuff, we're basically going to take these ideas of shapes and combine them with what we've been learning in Math 1 and kind of place them onto the coordinate plane. So our first new idea is this distance formula. Okay? So it looks pretty complicated at first, but we're going to make it a little bit easier. So the distance formula, what it does is it takes the distance between any 2 points. So if I had 2 points, you may want to kind of draw this. I can draw them anywhere. So we'll call this guy x1, y1. And we'll call this guy x2, y2. And so what the distance formula does is it provides us with the distance between that line. We cannot count. The reason we can't count is we're going diagonally. Right, if I had two lines across, right, like if this was at -2, say like -3, and this was at, 0, -3, because it's just a straight line across, now I can count. I can count like over 1, 2, right, so that distance would be 2. But when we're going at a diagonal, you can't count diagonally, so you have to use this formula. So the formula, we just subtract the 2 x's and square it, and then add on, subtract the 2 y's, square it, and then at the end, take the square root. So make sure we're doing PEMDAS here. Right? And even though, the square root counts as an exponent, but what you want to imagine is there's like a really big parentheses here inside a square root, so you have to do everything inside the square root first, and then the square root is going to be your very last step. So kind of doing an example. Okay, if we wanted to find the distance between the points -3, 2 and 4, 6. So I'm going to just label this x1, y1, and x2, y2. So our distance formula, we would do the square root of 4 minus -3 squared plus 6 minus 2 squared. That would get us 4 plus 3 is 7 squared, plus 6 minus 2 is 4 squared. That would be 49 plus 16. And that would be the square root of 65. Now, we can leave our answer in radical form like that. That's a perfectly fine answer for Math 1. If we did want to make it into a decimal, we could also use a calculator to make it into a decimal. I do want you to kind of realize, hopefully we know our squareds. So 1 squared, 2 squared, and so on. So hopefully we know that. So I just sped this up so we could kind of have a picture of it. But we should really have all of these 1 through 12 memorized. Okay, it's a really good idea to have 1 through 12 memorized. And so if we kind of knew that 8 squared was 64 and 9 squared was 81, well, if I was going to do the square root of 65, it's just going to be a little bit bigger than 8 because 64 is a little bit bigger. 65 is a little bigger than 64. So it's probably going to be like 8.1, 8.0 something. And if you type that in your calculator, you will actually end up with 8.0623 if we went out to 4 decimals. So either one of those two is a correct answer. And so that's kind of how we do these. So, that's great and all, and we can use that formula every single time. But I have a way that I like to do this way, way, way better. Okay? Now, in order to do my method, and I really like my method, I think it's way easier, but the first thing we need to do is we need to graph it. So if we graph it and we draw a line between them, I want us to kind of think, what shape could we make? What do you notice about what shape we could make, we could kind of draw in here? So we can draw in a right triangle. So you can either go, across this way, and then up, or I could have gone, up first and then across. That could have worked as well. So I could make either one of those two right triangles. But as long as you need to go from one point, basically left and right, and the other point up and down, that will always turn this into a right triangle. And so now, these horizontal and vertical lines, we can count those. So if I just count it over 1, 2, 3, 4, 5, 6, 7, that's a distance of 7. If I count it up 1, 2, 3, 4, that's a distance of 4. And so now we can go back to our 8th grade math of a squared plus b squared equals c squared. Right? C is always the longest side across from your right angle. So this definitely, I really expect that you guys know a squared plus b squared equals c squared. If you don't, it's a very easy formula. It's called the Pythagorean theorem. If you really feel like you've never seen this or completely forgot it, I would encourage you to just jump on YouTube after this video, or even pause this video right now, and just YouTube Pythagorean theorem and make sure you understand kind of the general concepts of it. So a and b can be any of the other two numbers, but c has to be our biggest number. So we're going to do 7 squared plus 4 squared equals c squared. Okay, 7 squared was 49 plus 4 squared is 16 equals c squared. That's 65 equals c squared. And then to get rid of the squared, you square root. That's how you undo a squared. Right, like in math, if I have x plus 2 equals 6, the inverse of plus 2 is minus 2. You always do the inverse operation to cancel it out. So when you square a number, like if I took any number, like say I picked 6, if I squared 6, it's 36. How do I undo that? If I square root it, I go back to 6. So that shows us that when we do squared and square root at the same time, they cancel out. So this ends up just being the square root of 65 is c, and that was the answer we were looking for, right? So in this case, the c is the distance, okay? So our distance, we would say, would be the square root of 65, or, type that in a calculator, we got that 8.0623 number. So either one of those two answers is correct. So I really like this method a little bit better. And you can kind of see what happens is, if we look back here, 4 minus negative 3 was what gave me 7, and 6 minus 2 is what gave me 4. And that's kind of what you do on these, right? This is 6 on the y, and 2 on the y. And so when I count, it is 6 minus 2. That's y2 minus y1. So that vertical distance will always be y2 minus y1. And then this horizontal distance is 4 minus negative 3. That's always going to be x2 minus x1. It doesn't matter which order you subtract, by the way. it doesn't matter which point you call x1 and y1 or which point you call x2 and y2, because when you square the number, it'll automatically turn it positive. So if you kind of think about that, is if I had done 4 minus -3, that gives me 7. If I had done -3 minus -4, that gives me -7. Now at first that looks like they're different, but when I square them, 7 squared and -7 squared both give me 49. So I wanted to point that out, is it does not matter which one you call x1 and which one you call x2. So here's kind of this, as a nice picture to kind of show us, is the distance formula is derived from the Pythagorean theorem, meaning if you start off with the Pythagorean theorem, the distance formula is just that with an x1 and a y1 on a graph. But what that means is we can always just go back and use our Pythagorean theorem to solve for the distance formula. And so that's kind of how I usually do that. So now we're going to apply that to shapes, right? So we're going to apply this to our scalene triangles, isosceles triangles, and equilateral triangles. So if we had a example where we wanted to classify a triangle as scalene, isosceles, or equilateral, we would want to graph that. So if you have graph paper, or you don't have graph paper, just kind of create a graph on your paper. One thing to always watch out for is what a graph is counting by. I'm just going to count by ones, but if it's not counting by ones, you want to be careful. So there's -3 and then up 2. So we're going to call this point A. I'm going to just put an A next to it. Then +1 and -1. I'm going to put a B there. And then +4. And then +6. Put a C up here. Okay, so just looking at this triangle, it definitely does not look equilateral. It could be isosceles, but it also could be scalene. I'm not 100% sure. Hypothetically, I could get a ruler and try to measure it. But we're going to just prove it, okay? I want you to prove it. So the way we're going to prove it is we're going to have to figure out the distance of all of those 3 sides. So, I'm going to first do the distance between A and B. And I'm going to use different colors for this just so we can kind of see it. It is a little bit of work here. So let's do the distance between A and B. So in between A and B, we're going to just make a triangle. So I'm going to go down and then over. So this is down 1, 2, 3, and then over 1, 2, 3, 4. And so I'm going to just do, for this one, right, I'm going to just say 3 squared plus 4 squared equals c squared. So that's 9 plus 16 equals c squared. That's 25 equals c squared. We're going to take the square root of both of them, and we'll get c equals 25. Or sorry, c equals 5. Next, I'll do the distance, how about between B and C? So again, I'm going to just switch colors. So I'm going to go over and then up. So this is again 1, 2, 3. But then this one is 1, 2, 3, 4, 5, 6, 7. Okay. So our distance between B and C, we'll do that same thing. We'll do A squared is 3 plus B squared was 7 equals C squared. So it gives me 9 plus 49 equals C squared. That's 58 equals C squared. And you'll type this into a calculator. You can actually leave it like that, but I'll type it into a calculator, get a decimal. And I ended up with 7.6158 is equal to C. So really this isn't C necessarily, it's the distance between B and C is 7.6. Right, and the distance between A and B was 5. All right, and then we'll do one last one for our third side. And so for our third side, I'm going to go up to get to that 6, and then across. So 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. All right, and so the distance between A and C is equal to, or we're going to just kind of do that formula again, a squared plus b squared equals c squared. And so we'll get 16 plus 49 equals c squared. And so that's 65 equals c squared. I think we already did this one, right? We got that 8.062 number. And so now we can see that they're all three different, and we want to explain this. So we'll say triangle, you can use that little triangle symbol, ABC is scalene because all three sides have different, I would either use the word measurements or lengths. So I'm going to use measurements, have different measurements. But you could use the word lengths as well. Don't say all three sides are different. You want to be specific. How are they different? They have different measurements. They have different lengths. Okay. When you do get good at these, by the way, I was starting off by literally writing this formula as like a squared plus b squared equals c squared. But when you get better at these, what you can do instead is you can literally just say the distance between a and b is equal to the square root of, now I still like to draw the triangle, but you can do, 3 squared plus 4 squared. As long as you're careful about, keeping that square root, doing 9 plus 16, keeping that square root, doing 25, and you get 5. So that's kind of an alternative way to write it. Some students will end up starting to write it this way, and some students just keep doing the a squared plus b squared equals c squared. Either way is okay. It's just kind of a preference. All right, moving on. What about acute, obtuse, or right? So we classified our triangle as scalene. Now we want to see if it's acute, obtuse, or right. So there's this new formula, and it comes from the Pythagorean theorem, but you need to make sure that you write the c squared first. Okay, write the c squared first. So if c squared is equal to a squared plus b squared, that's a right triangle. Right, that gives us a right triangle, and that's because, this is, the Pythagorean theorem only works for right triangles. But if we do c squared is greater than a squared plus b squared, that ends up being an obtuse triangle. And if c squared is smaller than a squared plus b squared, that ends up being an acute triangle. So in order to apply this formula, what we already have to know is we have to know a squared, b squared, and c squared. So you already know it. What you're actually solving for is you're solving for the sine. So the way that I like to write this formula is I like to write c squared box a squared plus b squared. And so then we're solving for the sine. We're trying to figure out, is what sine goes in there. So this is the only time we use this formula is if we're trying to figure out what kind of a triangle it is. So if we took our same triangle that we had before, and we want to figure out, is it acute, obtuse, or right? Now, we already have that triangle. I'm not going to regraph it because that's just going to take too long. But we already know that our three sides, actually maybe I'll pause and just go copy paste it. All right, so this is all the information that we had from our last question, right? This is the same triangle. So we had a distance of 5, 7.6, and 8.1. Now, the really important part about this formula, and you might want to add this on here, is that C has to be your biggest side. Okay, C is always our biggest side. The formula only works if you make C our biggest side. So in this, over here, what is our biggest side is the 8.1, so that has to be C. The other two don't really matter. So that formula is c squared box a squared plus b squared. Again, the time you use this formula is if they're asking us, is it acute, obtuse, or right? So I rounded my numbers to 1 decimal. That's fine for right now. 8.1 squared box, and then we're going to do 5 squared plus 7.6 squared. So you're just going to type these into a calculator. Now, if you're kind of smart about it, okay, you can actually come back here and remember that this was from the square root of 58, and this was from the square root of 65. So if we actually write it that way, I'm going to kind of show you a little bit of a trick. Is this was from the square root of 65, and then this was from the square root of 25, but we'll just leave it as 5 because it's a whole number, and this was from the square root of 58. What happens is those guys cancel. So this is actually kind of a good reason to leave your answer as a radical instead of putting it into a decimal. But if you had, done 8.1 squared, you would have gotten 65. If you had done 7.6 squared, you got 58. You're actually going to get a number kind of a little bit smaller than those, or a little bit bigger than those, like a decimal really close to it, because we rounded. But if you didn't round, you would get 65 and 58. So now we're going to add up 25 plus 58. Okay, and so 25 plus 58. What I kind of like to do is take 2 off of the 25. That's 23. To make it 23 plus 60. So you get 83. You can also use a calculator. So what sign goes in here is a less than sign. So a less than sign goes in there. So that tells me that this is an acute triangle. All right, now if we need to justify it or explain it, why? Because c squared was less than a squared plus b squared. So that would be our reason. All right. Moving on, we now want to think about our other shapes. So the other thing that we might need to do is think about parallel and perpendicular lines. Right? Parallel lines have the same slope. Perpendicular lines have opposite reciprocal slopes. We learned that a couple chapters ago. So now we're going to kind of take those and use it to talk about squares, rectangles, all those quadrilaterals. So this is an example from the homework. This is part C in your homework, number 1, and it says for each set of graph vertices, determine the location of the vertex D that would turn the figure into the shape. So we want to make a quadrilateral ABCD that becomes a square. ABCD, those are just naming the points. We have A, B, C, and then we don't know where D is. Now what we do know though is that for squares, our opposite sides are, all of our sides are the same length, and our opposite sides are parallel, and then our adjacent sides are right angles. They make a right angle. So when something makes a right angle, we have opposite reciprocal slopes. Now the easiest way to do this is just to kind of count. Okay, this goes down 1, 2, 3. All right, sorry about that, got a phone call. So we'll start that over. So we want to kind of think about the slope. So the slope is down 1, 2, 3, 4, 5, 6, left 2. So what I did there is I went down 6, and then I went left 2. Now, don't simplify it, leave it like that. What would be the perpendicular of that? The perpendicular of that would be up 2 over 6, right? So flip the sign and flip the numbers. So if I went, from C, if I went up 2, right, and then, yeah, so, oh, you know what, I totally messed this up. I realized why I messed this up. This is actually down 6, down 1, 2, 3, 4, 5, 6. Left 2 is actually minus 2. So I will simplify this to 6 over 2, right? And so, if you started at B, it's up 1, 2, 3, 4, 5, 6, and then right 2. So it'd probably be better to start at B here. But either way, the slope of this line should be positive, right? Because that line's going up and down. So it's up 6 over 2. So the opposite is actually, my fault, is down 2 over 6, right? Because if I flip the 6 and the 2, I get 2 over 6, and then it was positive, it becomes negative. So at B, if I go down 2 and then right 6, I get to C. So I want to flip it again. That goes back to 6 over 2. So up 1, 2, 3, 4, 5, 6, right 1, 2. So you can kind of do is that pattern is going to happen here, right? And then you can see the opposite pattern would be up to left 6, 1, 2, 3, 4, 5, 6, and that does connect it. If I went up to left 6. So that's where point D is. So we didn't even really have to do any math except for just counting. So where's that coordinate? Is at 7 and 4. So 7, 4. Okay. So our answer would be, D is at 7, 4. If we really need to explain it, how would we have explained what we did? What we did is we did the slope between A and B was 6 over 2. And so what's the line opposite of A and B is C and D. So that means the slope between C and D needs to also be 6 over 2. So we just counted up 6, right 2. Okay. So that's kind of what we did. All right. Now, this next one might be a little bit trickier. Is what if we wanted a trapezoid with only one set of parallel lines? Well, what a trapezoid is, right? That's kind of from the beginning. And we didn't really go over this, but I'll go over it now. is a trapezoid is any line. It could look like that. It could look like this. But it's basically where these guys are parallel, but then these other guys are not. Okay? So the key on a trapezoid is, do the same thing. So let's count the slope here. I'm going to start at B. It's always easier to actually start at your point to the left. If you start at your point to the left, it'll be easier to think about. I made that mistake on the last one. So if I start at B, if I go up 1, 2, 3, 4, then I go to the right 2. So up 4 and then to the right 2. Now, if I go up exactly 4 and to the right 2, what's going to happen is I'm going to get a square. But I want to make that line parallel, so I just need to do any combination of this. I can, divide it and get 2 over 1. And so I could do up 2 and over 1. And if I draw that, this will be a trapezoid. Okay, because these two lines are parallel and those lines aren't. But I could do any combination, instead of doing up 2 over 1, I could have done up 8 over 4, right? Instead of dividing each by 2, I could multiply each by 2. Okay, so I could have gone up 1, 2, 3, 4, 5, 6, 7, 8, and then over 1, 2, 3, 4. 1, 2, 3, 4. And what you'll see is that's kind of an extension of that line. Right, and so that's a new trapezoid. Looks a little bit different, but this also is parallel. The key is what I could not have done is I could not have gone up 4 over 2 because that would have made a square. Now, could I have also done it on the other side? Absolutely. So there are an infinite amount of right answers for this, because I also could have done, this guy between B and C, right? Between B and C, my slope is down 2 and then to the right 1, 2, 3, 4. So my slope is like -1/2, right? And so the opposite of BC would be at A, down 1 over 2. I could have done it that way, right? And that also makes a trapezoid. So basically the key here is, to find the slope, whatever your slope is. My A-B slope was 4 over 2. And then to do the sign opposite of A and B would be, C and D. Okay, so there's so many right answers. The right answers we had come up with were possibilities where the first one we had done was up 2 over 1. And so it was at that point 1, 0. That would have worked. Another right answer we did was that second one we did was here at 3 and 7. That would have worked. And then the final one we did was at -1 and 4. And that would have worked. So lots of right answers, but the key here is just to kind of figure out the slope and then make the opposite side parallel. But since we want it to be a trapezoid, it can't be a square. So we just have to do another combination of that slope, right? Instead of doing up 4 over 2, we do anything else. We could do up 2 over 1, up not up 4, but up 6 over 3, up 8 over 4, up 10 over 5, as long as that simplifies to the same slope. So then, here, this last question on the homework is going to ask us to determine if a quadrilateral is a trapezoid, square, rectangle, or rhombus. So we're pretty much right around 30 minutes. I'm going to try to do these last 3 examples fast. My trade-off is these are all from the homework. So we're going to do 3 examples from the homework. They're the odd ones, then you can do the even ones on your own. So A is at -4 and -2. I'm going to put an A there. B is at +2 and +4. I'm going to put a B there. C is at 8 and -2. I'm going to put a C there. And D is at 2 and then -8. And I'm going to put a D there. When you notice these opposites, that's a good hint that it could be a square or rectangle. But not always, so just be careful. So we have to actually prove this. The easiest way to prove it is by just counting those slopes. And so, if I go from A, I said use the point on the left. So if I go from A to B, okay, that's up 1, 2, 3, 4, 5, 6. And then over, oops. So I'm here, over 1, 2, 3, 4, 5, 6. So I get 6 over 6. Now don't simplify it, let's leave it there. Okay, now let's do between B and C. Okay. So starting at B, because it's more on the left, down 1, 2, 3, 4, 5, 6. And then I was right there, over 1, 2, 3, 4, 5, 6. Okay. These are opposites, right? And the signs are flipped. So those are perpendicular. Now, that only tells me that this is a right angle. It doesn't tell me it's a square yet. How would I figure out that it's a square? I would need to show that all of my sides are the same length. But the way I could do that is actually to figure out those other slopes. So let me do the slope between D and C. I'm going to start off with D because it's more to the left. Up 1, 2, 3, 4, 5, 6. And over 6. And then between A and D, if you count, you'll get down 6 and over 6. Because I didn't simplify these, and I see that that pattern's the same, I'm going to know that if I do that whole distance, is the square root of A squared plus B squared. Right? The distance of all of them is going to be the square root of 6 squared plus 6 squared. So the distance of all of them is 6. Every single one of these is 6 because they all have the same pattern of, up and over. Right? When you do that, this pattern, these end up being, your A and your B and the formula of A squared plus B squared. That's why I said don't simplify them. Right? Because if I turned any of these into that triangle, right, it's over 6 and up 6. So, A squared plus B squared equals C squared. So this ends up being a square, so we can say that this is a square safely because we showed that our opposite sides were our adjacent sides were perpendicular, and that we showed that all of the sides had a distance of 6. Okay, next one we have 1, 0. We have 2, 4. I don't want you to just say it's a square because it looks like a square. Okay, I'm not going to give you credit on this one if you just say it's a square without showing that word. You need to show that your opposite sides are perpendicular. Or sorry, your adjacent sides, meaning sides next to each other, are perpendicular. And then that all of the sides have the same length. Okay. So we have A, we have B, C is at 10, 2, and then D is at 5, -1. Okay. So again, looking at this, it looks like it might be a trapezoid. But I want us to actually show that, okay? I want us to show that. So how are we going to show it's a trapezoid? We need to show that the opposite sides are parallel. So the slope between A and D, I'm going to start at A, it's more to the left. Down 1, and then over 1, 2, 3, 4. So it's -1 over 4. What's that opposite one is between B and C. So between B and C, I would go down 2. And then over 1, 2, 3, 4, 5, 6, 7, 8. Now here we do want to simplify that, right? These are the same. So what we can say is AD and BC, when you name lines, you put a line over them, are parallel. If you want to shortcut that, just use the parallel. Now, this didn't tell me it's a trapezoid yet, right? I can look at the graph and I can tell that A, B, and C, D aren't parallel. But you need to show that mathematically. So let's just really quickly do those other two slopes. So the slope between A, B, start on the one more to the left, up 1, 2, 3, 4, over 1. Okay. And then between D and C, start the one more to the left, up 1, 2, 3, over 1, 2, 3, 4, 5. These are not equal to each other. So we could say AB is not parallel to DC. Remember, put the line over it. So then we could say, therefore, this 3 dots is a symbol for therefore. ABCD, that shape, ABCD, is a trapezoid. Right? Why is it a trapezoid? Trapezoids have one pair of parallel lines, and then the other pair of lines are not parallel. Okay, that's a trapezoid. All right, and then our next one, we have A is at -3, -3. B is at -1, +5. C is at +6, -2. And D is at 4 and -4. This was A, B, C, and D. Again, this looks like it's probably either a trapezoid or nothing, but let's just kind of go through and make sure. So this might even just be nothing. So when we look at this, Oh, you know what? I think I messed this up. It was -3, +3. -3, +3. Okay. So actually this looks like a rectangle when we draw it this way. But how do we show that something is a rectangle? We need to show that the two lines next to each other are perpendicular, and then we need to show that two lines opposite of each other have the same distance. So let's start off with the slopes. Let's do the slope between A and B. So I'm going to start A is more to the left. I go up 1, 2, over 1, 2. So 2 over 2. Now let's do between D and C. The slope between D and C. Okay, start at D, it's more to the left. Up 1, 2, over 1, 2, 2 over 2. So they're both, simplifying to 1. So AB is parallel to DC. Now, if you get 2 over 2 and 2 over 2, they're always going to be equal. Right, let's look at the last one. These had the same slopes, but see how it was -1 over 4 and -2 over 8? So they weren't equal. AD and DC, they're not going to have the same distances, right? They don't have the same, or BC, they don't have the same distances, but they do have the same slopes, right? That's because I had -1 over 4 and -2 over 8. They simplified to -1 over 4, but they were doing a different pattern. When I get 2 over 2 and 2 over 2, they're always going to be equal. But we need to show it really quickly. So let's just do, the distance between A and B is now up 2 and over 2. That's our, 2 and 2. That would be our A and our B. So if we did A squared plus B squared equals C squared, that simplifies. I showed you that shortcut to 2 squared plus 2 squared, which is the square root of 8. You don't need to simplify that. Now, the distance between D and C will also be the same square root of 8 because it's a 2 and a 2. So now we know that AB and DC are equal. They have equal measurements, right? So therefore, we can say that ABCD is a rectangle. Now we probably want to just show that it's not a square. So we probably want to look at, maybe A and D really quickly. So what would be the distance between A and D? Down 1, 2, 3, 4, 5, 6, 7. And then, I never showed the perpendicular. So actually I didn't prove it was a rectangle yet. All I proved right now is that my opposite sides were equal. So this is a parallelogram right now, but I didn't show it's a rectangle because I need to actually show that perpendicular slope. So this is actually good. So let's do the slope here. So I went down 7, and I go over, I think I miscounted. I think it's down 8. Down 1, 2, 3, 4, 5, 6. Oh no, okay. Down 7 and then over 7. Yeah, that makes sense. So then the slope between A and D is down 7 over 7, which simplifies to -1. This is +1. +1 and -1 are opposite reciprocals. So we could say, our line DC is perpendicular to our line AD. So now that we know they're perpendicular, now I know these are right angles. So now I know that this has to be a rectangle. Now, how do I know it's not a square? Well, looking at it, we know AD is not the same as AB, but if we just want to quickly show that with math, the distance between AD would be the square root of 7 squared plus 7 squared, right? The 7 and the 7. So it's the square root of 49 plus 49 is 98. That's not the same as the square root of 8, right? So we know that, DC is not the same length as AD. So now we can say, therefore, ABCD is a rectangle. Okay. But the most important thing on here that I did forget about at the beginning is we need to show to prove something's a rectangle, we need to show that we have that 90 degree. So how do we show that 90 degree? We do the slope of AB. We got 2 over 2 or 1. And we did the slope of AD and we got -1. That showed me that it was a right angle here. I actually didn't really even need to show that these two were parallel. I don't really have to do that. The main thing I have to do is show that right angle. Okay, but showing both of them is good. Showing all of this work is really proving every little step of it. So this is what I'm going to be looking for, is kind of that math showing me, that you're doing the distance formula, showing me that you're comparing the slopes, and that's going to be what proves that this shape is a rectangle. Obviously, we can look at it and we can think it's a rectangle. But sometimes what's going to happen is you get a shape that really looks like a rectangle, right? And it might look like a rectangle, but this guy is actually not a rectangle. Even though it looks really, really close to a rectangle, this one we can see is up 2 over 1, and this one is up 3 over 2. Sorry, up 2 over 2, and this one's up 3 over 2. So when we look at it, we might think it's a rectangle, but it's not quite one. So we just got to be careful and look at those slopes. Okay, so we just did our video number 1. Homework is going to be skills pages 118 to 123, and the Mathia for this one, and then you'll watch the next video. So the next 2 videos, I promise, will be under 30 minutes. This one was longer just because I wanted to go through those examples and because we had to review